Hello, the topic for today is finding the area between two curves. So remember, we found the area between a curve and the x-axis. Let's say I want this area by doing the integral of that function from wherever it started on the left to wherever it ended on the right. So now what we're going to do is we're going to introduce a second curve, let's say like this. And instead of wanting that area, I want to find the area between those two curves, like that, still from some beginning left x value to some end or terminal x value that we'll call b here. So this is what we want to do. We want to just take the idea we've already been working with and extend it so we're finding the area between two curves. So here's the integral, how you set it up. It's not that complicated, not that different than what we were doing before. This would be your leftmost boundary. This would be your rightmost boundary. And then this, our next lesson is going to be when we turn this on its side, but for today, this is the top function minus the bottom function. And one thing to be careful of is be careful if the bottom function has multiple terms. And that is because if this is like two terms, remember that minus has to distribute through both of them. If you're doing them by hand, you've got to distribute that minus. Or if you're punching it in your calculator, you have to put that in parentheses, both the terms, so that the minus is impacting the whole second function. All right, so let's look at our first example. We'll actually steal this kind of setup. Let me get rid of all this here. So for our first function, we're going to let f of x be 1/2 x plus 4, a line. And we'll let g of x be -2 minus x squared. So we're going to want to take a look at the graph. These are very visual problems, particularly as the graphs start getting more complex. You have to know which is the top function and which is the bottom. So you don't want to just like kind of knee-jerk just throw the functions into the integral. You want to be sure you know how they're oriented in relation to each other. So this is a line. It's got a y-intercept of 4, a slope of 1/2. So it's going to look something like this. And this is a parabola. It's opening down, and this shifts it down too. So it's going to look something like this. And the way I'll phrase this question is, let's say I want you to find the area between these curves from -2 to +3. So visually, that would be this region right here. We want to find the area in the green. So we get the setup, we see what we're looking for, now it's time to start setting up our integral. So this is my leftmost boundary from -2, that's hard to see. And this is my rightmost boundary to 3. This is where it begins, the region in question. This is where it ends, the region in question. Now my first function has to be the top function, which is the line. So I'm going to write 1/2 x plus 4. It wouldn't be wrong to put that in parentheses, but it's not necessary. But now the important part, now we have to take away the bottom function, which has multiple terms. So if I were putting this in a calculator, I could enter it like this, and that would be fine. That would work out fine. However, if I want to do a little bit of this manually, this would be 1/2 x plus 4, and that has to be distributed. And that's the key, is this has to hit both terms, right? And I could combine my like terms. And let's see, so we got x squared plus 1/2 x plus 6 dx. And then we would, here, we'll just put that in our calculator. And hold Hold on a second while I get to the right screen here. So I'm going to do an integral from -2 to 3. I'm just going to type what I see here. I could type this one or this one. That's your call. Plus 0.5x plus 6. And so I'm getting an answer of 42.92 units squared because it's an area, right? So as usual, you know, the number, we like to get an answer, but this is more about the setup. We have a top function. We've got a bottom function. What I need to capture that in an integral so I can put it in the technology or grind it out by hand. So it's top minus the bottom, and we're being careful about how that minus distributes or reacts with multiple terms there. So that's kind of our first example. It could just be two separated functions where you're told this is where it begins, that's where it ends. You would have no way of knowing where that is. The instructor of the book has to give you these values in a case like that. But now let's look at a situation where you get kind of an implied region. So I have to erase this. We'll get to example number 2. And we'll stick with the line in the parabola here. So let's do f of x is a half x minus 2. That's just shoved down a little bit. And g of x is 2 minus x squared. That's lifted up. So what I've done is I took the parabola and shoved it up here and the line and pushed it down there, which gives us that scenario. So here. Now notice the top function. Well, there's a few things to notice here. I think most people would realize this is kind of a natural region that you'd be talking about. That is the part we want. We want to find the area between the curves there. Now this one, we're not told what A and B are. We have to find A and we have to find B. Those would be the points of intersection. So manually, we could do that by setting these equal to each other and solving. You're free to use a calculator. Remember, when you do that, you enter them both in. You know, you have your y1 equals, and you put that in. And you do your y2 equals, and you put that in. And you want to do second trace. And then you want to find the intersect, right? So I think that's number 5. You choose that command. Now I already did this for this problem, and what I found was for A that was negative 2.266. That's an x value, and B was 1.766. So I need to find these points. Those are the x values for these points of intersection. All right, so that's all good. I got those points of intersection, and now I'm going to find my integral. So if I want that area, it's the integral from the beginning, that intersection point, to the end, that intersection point. And notice that the top function is now the parabola minus the bottom function is now the line. And if I don't put parentheses there, I'm in trouble. So I could enter that into my calculator. Now, if you have an older model, you can't just have these, this is y1 and this is y2. You have to clear that, and for y1, you have to put this in your calculator, 2 minus x squared minus a half x plus 2. You don't have to simplify, you can if you want. And you go and you graph it, and it won't look like that because, you know, if you want to see that, you got to enter that for y1 and y2, but we're altering it. We want this integral. So on the new calculator, you could just press your alpha windows and plug this in as you see it. If you do it on an older calculator, you got to plug this in, you press enter, and then you're going to press second trace, those buttons, and when you do that, you want to pick option number 7, which is the integral fx dx. And when you do that, then it's going to say low boundary, and you can type in negative 2.266 and press enter. and then it'll say upper boundary, and you'll type 1.766 in and press enter, and then it will compute the integral for you. So I need to punch this in real quickly to get our answer, so you can check it yourself while you do it at home. So I have negative 2.266 up to 1.766. I'm going to just enter it in like I see it. Minus 0.5x plus 2. Be careful of those signs. And my calculator is saying 10.92 units squared. Right, so it's not bad. You got to pay attention to what the top is, what the bottom is. This time I had, meaning you have to find these points of intersection so we have our limits of integration. All right, we'll try one more, and then that'll be the end of our lesson today. Again, our next lesson is going to be when we turn this on its side, and we'll be talking about left and right. We'll get there. So our next example is where the top function and the bottom function don't stay the same. So we'll do another line, a half x. This time we're going to use a cubic function. And if we look at that graph, this is the intercept of 0 and it's not very steep. And this will look like this. Now this creates two regions. This region in which the cubic function is the top and the line is the bottom. And secondly, this region where the line is the top and the cubic function is the bottom. See how they flip? They flip-flop there. So that means we got to set up two integrals for this in order to get our right answer. Otherwise, it'll actually tell us, well, it won't give us the right result. So what is the information I need? Well, to find that green area, I need this point, that's A, and that point, which is B, which it looks like and is in this case 0. So from somewhere, I don't know where, up to 0, those are my limits of integration, I have the cubic function is on top, and the line is on bottom, and since there's only one term, we don't got to worry about parentheses, right? I could combine those like terms, but I'm just going to let that fly. So how do I get that point? Well, I'm going to plug this into my calculator, y1 and y2, and I press second trace intersect, and then I find that point of intersection. Now I already did that, and I got minus 1.225. This is minus 1.225. And this integral right here will give me that area right there. Well, I'm only half done. I need this area also. Now that one begins at B, which is 0, and it ends at C. Now I suspect due to the symmetry of this, because, you know, look at the equation there, this is probably going to be 1.225, but I would want to check that. So this is still y1 and y2. I press second trace and I choose 5 for intersection. And when I do that, I get that C value, and it does in fact turn out to be positive 1.225. And I'll put my dx in. But in this case, the line is on top, and the cubic function is bottom, and that has two terms, so you better put that in parentheses. So this is going to be the integral of the green, this is going to be the integral of the red, and the total area will be the sum of the two. So I'll start pushing the buttons here. So my first integral, pardon the wait, negative 1.225 to 0. X third minus x minus 0.5x. Oops. Third minus x minus 0.5x dx. And for that one, I'm getting 0.562 plus, and my second integral goes from 0 to 1.225 0.5x minus x to the third plus x dx, and that's 0.562. We may have suspected that because of the symmetry of the situation, but you know, the next problem that won't be true necessarily, so you gotta, I would do it section by section. And we get our grand total area of 1.124. So that would be both of those put together. All right, so we'll play around with that a little bit, and next lesson we're going to turn things on their side. I hope you have a good day.